this video, I'm going to talk about equivalence relations. We did a little bit of this in class before the test, but I didn't want to just rush through it. I think it's an important topic. We need a little bit more than just what I did on, what was it, Wednesday. So equivalence relations. First off, we need to talk about different properties that relations might have. First one I want to talk about is reflexive. A set is reflexive is on a set A if for all A in big A comma A is in your relation. Everybody is related to themselves. So for example, if I had the set 1, 2, 3, 4, for it to be reflexive, I would need 1, 1, 2, 2, 3, 3, 4, 4. I need a loop at each point. So this is a reflexive relation. On the other hand, if I have 1, 1, 2, 2, 3, 3, and my set is 1, 2, 3, 4, it takes 1 to break it. This is not reflexive. The next property I want to talk about is symmetric. R is symmetric if whenever XY is in your relation, then YX is in your relation. So it has to go both ways. So for example, this one is reflexive vacuously. There are no pairings. There are no ABs, XYs, QRs to reverse. So everything that's in there has been reversed, kind of like every pink elephant in the room is wearing a tutu. That's a true statement because there are no pink elephants in the room. However, if I add one arrow here, 1 to 2, now this is broken. Now this is not symmetric because I've got 1 going to 2, but I don't have 2 going to 1. I can look at a third relation. This one is symmetric because I've got 1 going to 2 and then 2 going to 1. So these are 3 different relations: symmetric, not symmetric, symmetric. The last property I want to talk about is transitive. This one's a little bit harder to see on the graph sometimes. What this is saying is if X is related to Y and Y is related to Z, then X has to be related to Z. So it's kind of like a shortcut. Let's look at that same sort of situation. 1, 2, 3, 4, the empty relation. There are no X's related to Y's or Y's related to Z, so it is vacuously transitive. If I add 1 arrow to that, it's still transitive because I need 2 arrows to break the transitive part. So this one, I have 1 goes to 2 and 2 goes to 3, but I need a shortcut here for it to be transitive. So this one is not transitive. Let's see, I need a little bit more space for this. Here we are. So I need that shortcut in my path for it to be transitive. By adding 1, 3, I now have got 1 going to 2, 2 going to 3, but with the shortcut 1 going to 3, it is now transitive. So let's look at some examples and see which ones have what relations. The first relation I'm going to look at is the power set of the natural numbers. We're going to say that A is related to B if A is a subset of B. Well, is this reflexive? Well, yes, because every set is a subset of itself. Is it symmetric? Well, no, because just because A is a subset of B does not imply B is a subset of A. That's only going to be true if the 2 sets are equal. So this relation is not symmetric. Is it transitive? So if A is a subset of B and B is a subset of C, do I know that A is a subset of C? Well, yes, that's one of the things we proved. So we know that this relation is reflexive and transitive, but not symmetric. Next example, R's relation on the reals, we're going to say X is related to Y if and only if X times Y is positive. Is this reflexive? So for every real number, is X squared greater than 0? Unfortunately, 0 screws us up. Because 0 times 0 is not greater than 0, it's not reflexive. It has to be true for every single element in the set. Is it symmetric? If XY is positive, is YX positive? Well, yes, because multiplication is commutative. Order doesn't matter. Transitive. This one's a little bit trickier, but it's also true. If X is related to Y, so if X times Y is positive and Y times Z is positive, then X times Z is positive. For the product of 2 numbers to be positive, they have to be both negative or both positive. So they have to have the same sign. So if X and Y have the same sign, then Z has the same sign as Y, which means X and Z have the same sign. So therefore X and Z are positive. Another relation. This is a relation on the integers. We say x is related to y if and only if 3 divides x minus y. Is it reflexive? Is x related to itself? X minus x is 0, and everybody divides 0. So it is reflexive. Symmetric. Well, if x is related to y, that means x minus y is equal to 3k. But then y minus x is equal to 3 times that negative k. So yes, it will be symmetric because you just have to flip the order and put a negative in front of your k. Is it transitive? This one's a little bit harder to see. If x is related to y and y is related to z, that means x minus y is 3 times k, and y minus z is 3k underscore, because I couldn't figure out how to do an overscore in PowerPoint. If I add those two equations, I get x minus z is equal to 3 times crap. So therefore, x is related to z. So this is something that's, it's all 3 properties, and that is a very cool relation to have. In fact, we have a special name for it. Oddly enough, it's what this whole PowerPoint is supposed to be about. A relation on A is an equivalence relation if and only if it is reflexive, symmetric, and transitive. What happens when you do that is it breaks up the set into separate pieces. Each element has what we call an equivalence class or a congruence class. It's the set of all the elements that are related to it. X is in its own equivalence class because X is related to itself, and then all the other things it's related to is in its equivalence class. The set of all equivalence classes we will write as A mod R, and I'll sometimes call this X mod R because that's the canonical example is modular arithmetic. What do I mean by that? Well, let's go back and look at that example we just had where 3 divides x minus y. So what equivalence classes do I have? Well, let's just grab any old number in the integers. Well, I'm not going to grab any old number. I lied. I'm going to grab 0 because I like 0. Who's related to 0? Well, any multiple of 3 is related to 0. So the equivalence class of 0 is 3k where k is an integer. So let's look at 1 mod r. So I've got 1 in there. If I add 3, I have 4 and negative 2. Then I have 7 and negative 5. So basically it's 3k plus 1. It's everything that when you divide by 3, you get a remainder of 1, because when you subtract the 2, the remainders go away and you're left with a multiple of 3. And the last equivalence class is 2 mod r. That's anything of the form 3k plus 2. Now, when we're talking about the equivalence classes, we tend to use the smallest numbers. We tend to go 0, 1, up to whatever we're modding by, 1 minus it. In this case, it was 3. So the representative equivalence classes we tend to look at are going to be 0, 1, and 2. Though keep in mind, 0 mod r is the same thing as 6 mod r or 333 mod r. There are infinitely many choices for our representatives. So we kind of tend to stick to the ones that are close to 0 because we like zeros. The set of all equivalence classes, well, we've got 3 of them. So Z mod R is 0R, 1R, 2R. We use this structure so much, we have a shorthand for it. We call it Z mod 3, Z sub 3. Now, I can do this modular equivalence relation with any natural number. In general, if I did it with n, I would have n equivalence classes. I would have the 0, 1, I would have the 1, 1, all the way up to the n minus 1, 1. Oh, that's really hard to say. The equivalence classes were going to be 0 up through n minus r, and I can denote that z mod n. So let's look at some more equivalence classes, equivalence relations, sorry. I have A is the set 1, 2, 3. I let H equal 1, 1, 2, 2, 3, 3, because it's got to be reflexive, and 1, 2, and 2, 1. Now, for me, the easiest way to check something like that is to do a digraph. So I'm going to do a digraph of that. Now, when you look at a digraph, you know that it's going to be an equivalence relation if every chunk, connected chunk, has arrows going everywhere. I have a loop here, I have a loop here, 1 goes to 2, 2 goes to 1, everybody's connected to everybody. And 3, there's a loop 3. So this is an equivalence relation. I can look at the digraph and say, this is an equivalence relation. I have 2 connected chunks, and those represent my 2 equivalence classes. the equivalence class of 1 or the equivalence class of 2, whichever you want to call it, and the equivalence class of 3. Equivalence relations partitions the set. Now, a partition of a set is where you break it up into different sets. None of the sets overlap and everybody is in some set. You might have heard this in Calc 1. You probably should have when they talked about partitioning when you were doing integration, but it probably went right over your head and you forgot it. So partitions when you just break up a set and there's no overlap. The next example I want to look at, my husband teased me. For some reason, he thought this looked like lady parts. I don't think so. Well, yeah, maybe I do. Okay, so let's look at this. I didn't say what A is, but it looks like A is 1, 2, 3, and 4. Notice I'm looking at the 1, 2, 3 part. Everybody's connected to everybody. I've got 3 going to 1 and up and back. 2 is up and back. 3 is, I mean, everybody's connected, going both directions in this section over here. So that's one equivalence class. And 4 is all by itself. So it's its own little equivalence class. That's fine. So those are my 2 equivalence classes for this. We will work more on this in class on Monday and do lots of proofs and all that kind of good stuff. Hope you had a good weekend. I will talk to you later.